All right, let's talk about one of the most fundamental problems in all of computer science. It's a riddle, really, about trust and betrayal, and it's secretly the reason our entire digital world even works. Hey everyone, and welcome to CodeAccessHub. This is the place where we take really complex tech ideas and make them accessible to, well, everyone. Our whole goal is to break down stuff just like this into lessons that are clear, practical, and actually make sense. So, to really get our heads around this, let's start with a game. Have you ever played something like Among Us or Mafia? You know the setup. You've got a team of honest players just trying to get a job done, but there are a few imposters hiding among you, and their only goal is to cause chaos. Well, it turns out that whole game of trust, deception, and coordination isn't just for fun on a Friday night. Nope, it's the perfect way to understand a massive challenge that computer systems have to deal with every single second of every day. This challenge has a name. It's called the Byzantine Generals Problem, and it's all about one thing. How do you get a group to agree on something when you can't trust everyone in that group? So imagine this. A bunch of Byzantine generals have a city surrounded. They have to decide, together, on one single plan. Either they all attack at once, or they all retreat. Any kind of split decision, and they're doomed. But here's the catch. Some of the generals are traitors, and they will actively lie to make sure the loyal generals fail. And this isn't just some old fable. This problem was formally laid out in this groundbreaking paper from 1982 by computer science legends Leslie Lamport, Robert Shostak, and Marshall Pease. They basically wrote the rulebook for this digital battlefield. And the rules are super strict. 1. All the loyal generals have to end up with the exact same plan. 2, they can't just have a group chat. They can only send messages through individual messengers. 3, the traitors can and will lie. They can send one general an attack message and another a retreat message. And 4, this one's crucial. If all the good guys already agree on a plan, the traitors can't trick them into changing their minds. Now, on the surface, that might sound solvable, right? But it is deceptively difficult. In fact, under some very specific conditions, it's actually mathematically impossible to solve. Take a look at this. This diagram shows you the simplest impossible scenario. With just 3 generals in total, if one of them is a traitor, you just can't guarantee consensus. Think about it. What if the main commander is the traitor? He tells one general to attack and the other to retreat. Now what do the 2 loyal generals do? They have conflicting orders and absolutely no way to know who's telling the truth. They're stuck, paralyzed. So if it's impossible with just 3 players, how does anything in our complex world ever get done? Well, it turns out the moment you add more players to the game, solutions start to emerge. And there are 2 main paths to get to that agreement. But before we get to the solutions, you might be wondering, why not just appoint a leader? Well, what happens if that leader is the traitor? They'd have total control. Okay, so what about a simple majority vote? That doesn't work either, because as we just saw, a clever traitor can lie strategically to split the vote, making different generals see completely different majorities.
Okay, so the first real solution is what we can call the database approach. It's a really clever system that basically accepts that some messages are going to be lies and then builds a process to overcome them through sheer repetition and communication.
So here's the big idea. Instead of trusting just one leader, the system rotates through different leaders over and over again in multiple rounds. In every single round, everyone broadcasts their opinion to everyone else. This lets each general build their own local majority view. So, if a general gets 10 messages from his peers saying attack, he'll know to just ignore the leader for that round if that leader suddenly says retreat. It's basically using the wisdom of the crowd to spot and override a single bad actor. Now, the second path is what you might call the blockchain approach. And this one is different. Instead of trying to find the truth in a sea of potential lies, it just changes the rules of the game to make certain lies impossible in the first place. It's like creating a perfectly reliable group chat by using a powerful crypto tool, unforgeable messages, also known as electronic signatures. This is a total game changer. With electronic signatures, a general can sign their message in a way that is mathematically impossible for anyone else to fake. So a traitor can't just lie and say, hey, General Bob told me we should retreat. Nope. General Bob's signed message is the proof. That whole category of deception is just gone. Okay, so this is a really cool puzzle, for sure. But why does it matter so much in the real world? Well, because these generals aren't ancient warriors. They're the computers that run pretty much everything we do online.
You know, we tend to think of computers as being perfectly reliable, but when you're operating at the massive scale of a company like Google, that idea just completely falls apart. Just look at this quote from Jeff Dean, Google's chief scientist. The numbers here are just staggering.
If you actually do the math on that, it means you can expect a failure somewhere in the system every 5 minutes. Let that sink in, every 5 minutes. And each one of those failures, a server crashing, a corrupted message, a network hiccup, it looks like a traitor to the rest of the system. This is why your Google Doc is safe. It's why your files in the cloud don't just disappear. Your data isn't just sitting on one computer, it's copied across hundreds or thousands of them. And those computers are acting like our generals, constantly running these protocols to agree on the one true version of your data. This amazing ability to keep working even when parts of the system fail is called Byzantine fault tolerance. And of course, this brings us to crypto. This is the absolute core challenge that cryptocurrencies like Bitcoin were built to solve. How can a global network of computers that don't trust each other agree on every single transaction without a central bank or authority in the middle? The answer is a really clever solution to the Byzantine Generals Problem. So there you have it. That's the core idea behind this truly foundational concept in computer science. Now, this topic goes deep, and we've really just scratched the surface. We've got to give full credit where it's due. This explainer was heavily inspired by an absolutely fantastic video on this from the YouTube channel Polylog. Seriously, if you want to go deeper, you should definitely check them out. And if you want more breakdowns of the complex tech that quietly powers our world, well, you're in the right place. You can find us right here on YouTube at CodeAccessHub. If you got something out of this, please hit that like button, share it with a friend who's curious about this stuff, and of course, subscribe and ring that notification bell so you don't miss our next deep dive.
We'll leave you with this last thought. The Byzantine Generals Problem is the perfect example of an invisible problem. You never see it, but its solution makes everything from online banking to social media possible. So what other invisible problems are out there quietly holding our digital world together? Let us know what you think down in the comments.